Hi everyone, this is the third video in this series about analog circuits. And in this one, I'm documenting my thoughts around log amplifiers, anti-log, and using that to multiply two voltages together. So natural log of x, e of x, and then something like x squared, which is x times x. So first of all, let's have a look at what a log function actually looks like. So I will run the simulation, and then do this, and I'm going to go -5, 5, and 1. So this is just set up to see what ln of x looks like. As you can see, something to note is that at y equals to 0, this x-axis intercept does not intercept at x equals 0. So it intercepts at exactly 1 volt in this case, because ln of x when x equals 0 is actually negative infinity. However, in a log amp, that won't exactly be the case. So how does a log amp actually work? A log amp works by putting in a component into the feedback network of an op amp, which changes its current exponentially with the voltage across it. So that's how it introduces this log calculation into the circuit. I'm not going to go too deep into the math in this video because I think a lot of other videos do that really well, and there's a lot of good articles on it. But briefly, we can look at the Eber-Mols equation of a transistor, and also the Shockley diode equation of a where is it? Sorry about that. Yep, here it is. The Shockley diode equation of a diode, and as you can see, the current across the diode is related to the voltage across the diode through an exponential relationship. It's not exactly an exponential relationship because there's this -1 here, and also it's being multiplied by a bunch of stuff and divided by this sort of NVT, and that's why if you put a diode here and you measure the voltage across it, it's not exactly a exponential curve. So it intercepts the x-axis exactly at 0 volts, unlike a true natural log. And it's scaled and transformed in some ways because of the other constants. So you have to adjust for that if you want to calculate exactly natural log of x by calculating what the resistor values are and things like that. So I've showed you the natural log with a diode because it's created a negative feedback. In inverting config, we have to invert it again in order to produce actually log of x and not negative log of x. And then in a lot of circuits, you'll commonly see the diodes being replaced by a transistor where their base and collectors are tied together like this. And the reason why it's done this way is because the transistor is able to model the exponential function better than a standard diode. The reason is because the Shockley diode equation has this n factor for diodes. This is the ideal factor, which is basically the emission coefficient, and that's 1 for transistors. Transistors are designed for this to be as close to 1 as possible. And in diodes, this is not 1, it varies. And what's worse is that it varies with current, especially when the current is small. So when the current is small across the diode, what happens is the recombination in the p-n junction, it's depletion region, which is like basically a minority carrier, like a charge flies through and then it falls into a hole. So a lot of recombination happens compared to diffusion, which is the charges fly straight through. So when the current is low, the holes are not saturated, So there's a lot of recombination happening. And with diodes, this changes this emission coefficient. So because there's a lot of impedance going on, right, because of recombination, the voltage drop actually increases more than the standard n equals 1, which happens in a transistor. So in a transistor, what happens is because the base is so thin, the amount of recombination going on is minimal. And this is also why you see NPN transistors use more than PNP for these sort of log amps. The next thing I want to talk about is why is it that we can't just put the input into the non-inverting config and just ground the inverting config? Does that produce a log? And the answer is yes, it does. But because now the voltage across this transistor, and we have to obviously switch the direction because it's going to flow the other way, now the voltage is V out minus V in. So it's no longer minus 0 volts in the virtual ground. So the output is actually not just a log. You have to actually now minus V in here. So minus V of in 1 in this case. And you can see now this again will follow a closer to a log equation. So, if you wanted to use this non-inverting config, you would actually have to have a subtractor circuit after that to minus log of to minus the input voltage. So you might as well use the inverting anyways. So there's a lot of optimizations that you can do to get this as close to a log equation as possible. So I want to quickly talk over some of them that I see. The first one is you can ground the transistor space instead of having it tied to the collector. Why is this better? Because in the Eber-Mose equation, you can see that it's approximating IC, which is the collector current. And in order for that to work, the collector current needs to actually equal the current flowing through the resistor in series. So the current through the resistor has to be exactly the same as the collector current in order for the modeling of this circuit to be close to the Eber-Mose model. For the transistor. However, if you tie the base to the collector, some of that current which flowed through this resistor is going to flow right to the base and not through the collector. So by tying the base to ground, you actually make it better that way. There are some disadvantages with tying the base to the ground. For example, you can introduce other noise and things like that. But anyway, so the next thing is sometimes you'll see this diode which shorts the emitter to the ground, and the reason why that's added is because the transistor is polar, so the voltage can only flow, the current can only flow one way. And if this log amp is connected to a second stage, which is very common in other parts of the circuit, if this op amp doesn't turn on when the other parts of the circuit turns on, you can end up with a high voltage flowing through here, and there's no place to flow through here because the op amp might not be turned on, and then it has to go through this way, and that can actually break the transistor. So let's say if the voltage drop across here exceeds let's say 10 volts, it can actually just reverse bias this this PN junction through a Zener breakdown or avalanche breakdown, and it can damage the transistor. So therefore there's this diode here that shorts at the ground. In normal operation mode, the voltage here is always negative, so it's always below ground. So therefore you can never actually have this diode activated in normal operation, steady state. The next thing I want to talk about is this sort of temperature compensation circuit. So what actually happens in the Eber-Mose equation is when you simplify everything, there's this IS, this reverse saturation current factor, and this VT, the thermal voltage, and both of these vary a lot because of temperature. So what ends up happening is you have to add in compensation to take care of this. So the way that it's done is that the So let's have a look at how the reverse saturation current is removed. In mathematics, ln of a divided by b is ln of a minus ln of b. So in this case, it's going to be ln of vi divided by r1 minus ln of is. So if you just have a circuit that plus ln of is back into the output voltage, you can adjust for this is, which changes a lot because of temperature. So that's what this circuit is doing. It's essentially putting a identical transistor in series, right, with the original output, putting a constant current through, and then you can adjust the constant current, figure out the equations and derive what it should be, such that it minuses the ln of is out of that equation to adjust for temperature. And then likewise, there's usually a gain stage at the very end with a temperature-sensitive resistor to adjust the final multiplication that you want to adjust your output on. And that is because Vt is also affected by temperature. It's linearly affected. So, and Vt is proportional to Vo. So by basically multiplying the output, you can adjust for the difference in Vt that changes with temperature. Cool. And so lastly, I want to talk about this thing. So this is a bit confusing. Why is there a capacitor and a resistor in the feedback circuit? And I had a deep dive into this. And the reason is because when your feedback is so high, and you might be confused, like, okay, well, isn't a log of a function going to be smaller than that? And so why is the feedback considered high? Well, the feedback is high because the proportion of voltage fed back compared to the proportion that's output is actually very large. So the proportion that's output is logged, right? But the proportion fed back is actually exponential. So it's actually a very high amount of voltage that's fed back compared to what's output. And because of that, what happens is op-amps have an inherent problem with stability if your feedback factor is extremely high. Because when it's extremely high, the gain bandwidth product, which is how much the op-amp can amplify signals at various frequencies, at very high frequencies, the gain bandwidth product does not drop below 1 when it's multiplied by the feedback factor. And that causes an oscillation. Because what happens is, at very high frequencies, if your gain bandwidth product multiplied by the feedback doesn't drop below 1, it feeds back the signal, but also it feeds back the signal at a 180-degree inversion because of parasitic capacitances inside of the op-amp. So because of parasitics, the signal will come closer and closer to a 180-degree inversion when the frequency of small signal inputs increases. So when there's noise in the circuit, it can come to a situation where the feedback is above 1, but also it's inverted 180, so it actually ends up adding to the input instead of minusing. Instead of it being a negative feedback, it becomes a positive feedback, and that creates an oscillation. So this capacitor and the resistor is used to both damp the feedback and also filter out any small signals which could be generated. And obviously we know that PN junctions inherently are very noisy. They have a lot of Gaussian noise and all this stuff. So yeah, that's what that's for. And yeah, so lastly, I want to talk about, before we move on to multiplication, I want to talk about antilogs. And antilog is very simple. It's just when you swap the position of the diode compared to the resistor, so the diode is connected in series and the resistor is connected in feedback, that creates a antilog effect, or like close to e to the power x. Again, it's not going to be exact because the Shockley diode equation has a lot of these other factors in it. And there's actually a problem with this, which is if you look at the output, right, you can see there's this drop and then there's something happens here. What happens here that destroys the output characteristic is that because it's exponential, there's a lot of voltage changes going on in the circuit, and the diodes can only support a certain amount of voltage drop across them before they start failing. So because the input and output are the difference is so large, having this diode means that as soon as my voltage difference across it exceeds the diode's limit, which in this case I think for this model is like 0.8 volts, it just starts to fail. It just starts to not be able to conduct any more current. And so you get this sort of response. It's not going to the negative rail. The negative rail is at negative 100 volts. So what you need to do is you need to scale down the input to that sort of 0 to 1 volt range in order to simulate a good output. And likewise, this also happens with a tied transistor because the BE voltage drop on this PN junction cannot exceed a certain limit, like 1 volt, for example. So lastly, let's look at the multiplication circuit that I said about earlier. So I'm going to demonstrate that it works first of all. So here I have an input, two of the same inputs, so this is basically x squared, and the output, it's linear, right? The input, and the output, as you can see, it's very close to x squared. So here at 5 volts, the output is 25 volts approximately, and at 10 volts, you can see it's 100. So how did I construct the circuit? Well, it's basically using the mathematical properties of logs. So log A plus log B becomes log of A times B. And if you anti-log that, so e to the power of that, it becomes A times B. So therefore, if you log this, add them together, and then anti-log it, that becomes this times this. And they're both x, so it's x squared in the output. Two things to note. One is, if you just construct it like this without this third adjuster circuit, you'll never actually get this exponential output. It'll be so different because, like I said again, the Shockley diode equation has all of these factors. There's this -1 here that we've approximated out. There's this, divided by VT, there's this N, there's this IS. And even if you used, all of the optimizations I talked about earlier, that's still going to cause problems because you can't optimize away a lot of this stuff. So VT, for example, you can't optimize away. IS, you got to compensate in a different way. So what I did is I added another circuit to basically subtract away some of this error. Because when you log A divided by B or log A times B, if you add that out, it becomes log A plus log B or log A minus log B, right? And so that error in the minus or plus log term, you can cancel it out using a third log that minuses them. So this log circuit is inverted. It's N3 is the invert of 1. I can demonstrate that. So N3, as you can see, it's the inverse of 1. And you can construct this by basically putting an inverted amplifier to put in 1, but I couldn't be bothered doing that. And I just adjusted these resistor values so that it approximates and cancels out all of the unwanted terms in the logs before I feed them into the summation circuit together. The last thing I want to talk about is, in some circuits, you won't actually see them using the summation circuit like this. In some circuits, I actually see them using something like this, where instead of having the base transistor grounded, they actually just feed the output of one stage to the base of another. So for example, if they want to add, they put it through here. If they want to minus, they put it to the transistor of the anti-log circuit. And this works because the voltage of the output is VB minus VE. And it's VB minus VE. And normally it's 0 minus VE, right? So therefore, the output is just negative of some input. But if you add a voltage here that's not 0, it ends up being V output of this minus the output of that. So it ends up becoming a summation or a subtraction. So that's why when you sometimes see something getting fit into the base, for example, let's say there's a power source of like exactly 1 volt feeding in here, or in this case, a secondary circuit being fed in, that's essentially just adding or minusing a voltage to the output. So yeah, that's it for the video.